things that we've been doing so far to a point. Let's see if I try this one. Copy. There we go. So again, you want to think about what is given and what we need to show. Okay? So this is how you want to think about this proof. Let's say this is some preliminary work. It's not part of the proof. This is how you should be thinking. You need to show that P divides the product of N and M. Right? So this is your last line in the proof. Therefore, P divides N. Right? That's how you want to end this proof. Well, now what gives you the right to say that P divides the product N and M? That means there is some other natural number such that P times that natural number equals Nm, right? So the line before, and this is just me kind of talking. This is not a proof. It's just kind of seeing what we're trying to get. The line before should be, therefore, there exists Q among natural numbers so that Nm equals PQ, right? That's what you want. Okay, well now let's see what is given to us. What do we have? Yeah, so we know that P divides N. So let's try to think about that. So since P divides N, what does that mean? Yeah. So then there exists natural number Q. So that's, right, so N equals PQ, right?
Does it matter what order you write that in?
Not really, yeah. So this is my N, by the way. I don't know, the marker is really off today. Or we need to calibrate it a little. Okay, so you have this line, right? Now keep in mind that this is what you want, right? Then you can always say, well, therefore, Nm equals, you can replace N with PQ. PQM, right? Now, I probably should have used that Q1 over here the way we've been doing this so far, right? That preliminary Q. That doesn't matter how you label it. Well, what is Q1 times M? It's just some other natural number, right? Since both, I'm going to calibrate this thing in a little bit. Since both M and Q1 belong to the set of natural number, we conclude that Q1M also a natural number, right? That product has to be a natural number, so let Q equals the product of Q1 and M. So therefore, Nm equals PQ. Right? And we're done basically, right? So you got that, you got this line. So therefore you get the last line. And then you kind of make it nice and pretty.
I just get lost where you just say that Q1 and M is Q.
Yeah.
Well, because you can always, it's a product of two natural numbers, so it's just some other natural number. Okay, that, because you're trying to fit it into the definition almost perfectly. So that's about it. I mean, you can just say, well, since, I mean, that's allowed to just say, well, Q1M, that's a natural number. So we're done. And M equals P times natural number. So
And then do we just get that
Yeah, so we just use that definition one, so it's a divide, so it divides the product. Let me,
Yes, so since we're multiplying two natural numbers, that has to divide m, or p has to divide m by q.
no,
I'm just confused. It seems like we proved that m's a natural number. I'm not sure where we proved that p divides.
well, this is the part where we prove that P divides, because we're trying to prove that P divides NM, right? In order for us to prove that, we need to show that NM can be expressed as a product of P and some other natural number, right? Well, here we have P times a product of two natural numbers. We're already done at this stage, because the product of two natural numbers is another natural number. And this is what I'm doing here, just to say that, well, the product of Q1 and M is just some other natural number. So now I'm replacing Q1M with that Q, so then it's clearly, you can see that NM is P times Q. So P divides NM then. And that's what we had to show, P divides NM. You don't have to do this part. You can just say Q1M is a natural number, so I'm able to express NM as a product of P and something else. That's really all there is to it. That makes sense?
That's all.
That's all. Let me see if I can calibrate this thing a little bit. The syllabus on Monday, but for now there is a slight change in that syllabus, and that's in the office hours, because right now we have office hours. So Monday, Wednesday, Friday, noon to 1, and Tuesday, Thursdays. Well, actually, it is better now. It's writing better. Tuesdays, Thursdays, 9 to noon. Now, 9 to noon is in the learning lab. Now, Monday, Wednesday, Friday, your syllabus says the office hours are in my office in 235. I'm actually going to do them here. So it's going to be, so this is the only change in Bristol 119 in our classroom. Because I have a class here till noon, and then I have to save all those videos, and it takes me a while, so and it has more room. Okay? And my office is a mess. Okay.
Oh, when you were talking about, were you just joking about that?
No. Are we going to do it? You want to sign up? How many? Yeah. Who wants to be in a math club? We just started a math club yesterday. Want to sign up for math club? Well, yeah. Can anybody give me a real piece of paper? We're going to have fun in that club. Yeah, just if you would like to join, put your name down and your email, and when we all ready to go, schedule a meeting. It's going to be a fun club. So yeah, I think I got about 6 people sign up for that yesterday at that club fair, so we might actually get it going.
Well, in my last college, they had like an engineering,
Yeah.
where it was just the engineering kids would get together, math, class and everything.
Yeah, I think again we'll do it's yeah keep passing it around. Maybe we'll get anybody else would like to join.
What days do you think?
I don't know yet. We're gonna get together and talk about it. But things that I want to do, like one of the things I want to do, like like a problem over a week context with some prizes. We'll just maybe put it on the website somewhere and get people from town sending us solutions. We used to do that. We used to put a problem in the pilot, like once a week. But then the pilots stopped doing that. They were cutting down on their puzzle section. So it was either keeping Sudoku or Math Club. So we'll try to do that. I'm thinking about, again, as a Math Club, comes finals week, we might provide some extra tutoring to our fellow students, because we have to do that. It has to be like service to college, so that's that. Service to community, well, that's a puzzle of the week thing. and then we'll just talk math. Well, maybe giving them little gift certificates, because they'll give us some funds, and we might buy a gift certificate to like whatever. Yeah, and so things like that. And again, whatever you like to do, we'll be able to do. Um, okay. So again, this we're gonna stop doing the silly math pretty soon. We're gonna start doing, um, we're gonna get into trigonometry next week. I just want to get through a few more fun little proofs, and then we'll, yeah, I'm pretty sure we're gonna just start doing trig next week. What do you mean by real calculator? Not necessarily. You'll be okay without a graphing calculator. You need a scientific calculator. So it's basic calculator that looks like this, that has, natural log button and like sines and cosines. Okay? So at home, sure, on the exams, you will need it, because you cannot use your iPhone calculator on the exam. No. Because you can do a lot of things on that calculator besides, on that phone. You can borrow a calculator from me. We have a few calculators we can lend students. Sure, I can hook you up with a graphing calculator. Cool, I'll do that. Anybody else use a calculator? You need one? I'll get you one too. Well, I did that last semester, and I'm still missing like 4 or 5 calculators. Actually, it's expensive. I know. But yeah, for this class, you don't need the graphing calculator. But you need a scientific one. And when we had the Dollar Tree store, we no longer have that. But you can buy a scientific calculator for $1 there, and it did all the sines and cosines. It was very awesome. It was a little calculator. It said calculator on it. It didn't have a brand. It said, yeah, calculator. And we tested it, and it worked. It matched the fancy $100 calculators as far as computation. It's $1 calculator. Can't beat that. But yeah. So, but as far as graphing goes, like for example, if you're working on a graphing problem and you do not have a graphing calculator, but you would like to check your answers, there's a lot of stuff you can do online. There's this thing called fooplot. We discovered that last semester. It works really well. You just kind of plug in functions, whatever the function you want to graph, you just type it in, like 5 times x cubed minus 3 times x squared plus, this is how you do e to the x. You do exponential x. And you can say, well, add the graph of that function. It always keeps the x squared for some reason. You just get rid of that. So this would be the graph of that silly thing. Okay, so you can just do that. There's another awesome tool called mathematical visualization toolkit, and it's a really, really awesome name because it abbreviates to MVT, and MVT is actually a very famous theorem in calculus. It stands for mean value theorem, and those people at CU Boulder decided to get all cute with us and build this program, and they tried to fake the name MVT, so that's where mathematical visualization toolkit comes from. And this thing is, well, this computer is a little cranky as far as running Java stuff, but it's really good. It does some things that your basic graphing calculator won't be able to do. Yeah, I cannot show you on this computer. It just doesn't allow me to do the Java things. But it will plot 2D, 3D. It will solve equations. It's just a really powerful tool. You can download it as an app on your computer. It's really good. Okay. But as far as the exams go, you won't need like a graphing calculator test. The scientific one will do, but you're allowed to use a graphing calculator. No problem there. Okay. Want to do a fun problem? Now I'm afraid of my fun problems. What if they don't work? I'm still trying to do the divisibility by 8 for those of you who came in late. I'm a little stuck on that one. For that previous one. Okay, so this problem is also in that packet that I gave you. This is a very fun problem. So find all 5-digit numbers that are divisible by 45 and oops, first 4 digits are consecutive. Is that how you spell consecutive? I think I was spelling it with a Q on Wednesday. Feels like a Q. Was I putting a Q in there? Yeah. Oh, I meant. Never mind. So does the problem make sense? You have a 5-digit number. First 4 digits are consecutive, 3, 4, 5, 6, for example, and the last one, whatever, has to be divisible by 45. Okay. So I want to find all such numbers. This is fun. Now, if I just tell you, knock yourself out, you use a calculator, it'll take us a while, right? But let's play with that. So it's not really a proof, but it's not really a problem kind of solution thing. But so we need some notation, okay? So let's say let P, which would be our number, is written like that: A, B, C, D, E. It's not a product, A, B, C, D. It's literally digits: A, B, C, D, E. Like 1, 4, 7, 2, 5, 5-digit number. Okay, so we usually use this notation, like I put a bar on the top, which means it's not a product of 5 letters. It's literally 5-digit number. So A is the first digit, B is the second digit, C is the third digit, D is the fourth digit, and E is the fifth digit. Does that make sense? Like, for example, don't write this down, but if it's a 3, 7, 8, 2, 1, so A is 3, B is 7, C is 8, D is 2, E is 1. That's what I mean by that notation, okay? So we can use some of the properties that we've proven already about the division. What we know that 45 divides P, right? Well, let's try this. Well, 45 is divisible by 5. Do you agree with that? So therefore, our number is divisible by 5 as well. Do you agree with that? We have a property like that, that transitive thing. I think the first property. Also, 45 is divisible by 9, right? Therefore, our number is divisible by 9. So our number is divisible by 5, and is divisible by 9. Do you agree with that? Okay. So since 5 divides 45 and 9 divides 45, I believe by property 1, that's the very first one that we proved, by property 1, 5 divides P and 9 divides P. Is that okay? So now, please tell me, since our number is divisible by 5, we know a lot about our number all of a sudden. What kind of numbers are divisible by 5? Yes, things that end in 0 and 5. So the only possibilities for E are 0 and 5. Do you agree with that? There's no other way we can have a number that's divisible by 5 if it ends in anything other than 0 and 5. So we really have 2 cases. We're going to do this problem by cases. Case 1, it ends in 0, and see what happens with that. Case 2, it ends in 5. and see what happens with that. Okay, so a lot of times we do that in math. Sometimes we just consider case by case and just go with that. Okay, so since 5 divides p, the only options for e are 0 and 5. Okay, so let's consider the first case, case 1, e equals 0. Okay, so therefore our number right now is a, b, c, d, 0, like that. Right, the last digit is 0, is divisible by 5. Now, is divisible by what else? 9. Now, how do we know whether the number is divisible by 9?
Divisible by 3.
Speak up. If you add up all the digits, it has to be divisible by 9. So a plus b plus c plus d plus, well, 0 has to be divisible by 9, right? So since 9 divides p, we know that 9 divides the sum of a plus b plus c plus d, well, plus 0. I'm not going to write plus 0. I'm just adding all the digits. 0 is, I can write it. It doesn't make any difference. See what I'm doing? Okay? Are we happy up to this point? Have we got this conclusion? Not happy? No, not at all. Because remember, what are we trying to do? We're trying to find all numbers that are divisible by 45 and first 4 digits are consecutive. Oh, I'm about 10% into this mess. But I'm messing with what's given to me. 45 gave me 5 and 9. 5 gave me 0 and 5, and I'm just looking at the first case of 0. I'll do case 2 when it ends in 5 and give me something different. But right now, so we got the divisibility by 5. That's what 0 gave us. Now let's see what divisibility by 9 gives us. And it gave us that the sum of all digits is divisible by 9. But what do we know about these 4 digits, A, B, C, and D? They have to be consecutive, right? So it's like 4, 5, 6, 7. So I can actually say that since A, B, C, D are consecutive, that means that our digits are, I can say that B equals A plus 1, because B is the next number from A. No, I think, well, because, well, A is A, and then the next one is plus 1. Then I can say that C is A plus 2, and D is A plus 3. Right? It's like 4, 5, 6, 7. If A is 4, then you get 5, 6, 7. Are you okay with that? That's what it means for digits to be consecutive. So therefore, A plus B plus C plus D can be replaced with A plus A plus 1, that's for B, plus A plus 2, that's for C, plus A plus D, I'm not D, 3. Right, this is what we mean by consecutive digit. Next one is one higher than the one before. So if actually combine like terms, we get 4A plus 6. Right? Well, but I don't know what A is. All I know that 9 has to divide this number, right? Because that's what this number is. Remember how we got to this point? 9 divides the sum.
Yeah.
Then we expressed each of these letters in terms of A by using the fact that the numbers are consecutive. So that's what gave us. Basically what we have right now, that 9 divides 4A plus 6. instead of writing a plus b plus c plus d. Well, now I just have to do basically trial and error to find the value for a that makes this work. What a can be? Well, be careful. A is just the first digit, so a is. It cannot just be all real numbers, because again, remember what a is originally. A is just the first digit in the number. So can a be 0? No, you cannot have a number that starts with 0. That's silly. Can a be 1? Sure. Well, you can have a number that starts with 1. Well, not in this case, because if you plug in 1, 9 does not divide 10. But potentially, could be 1, right? Could be 2, could be 3, could be 4. Can it be 5? Because again, it's 5, 6, 7, 8. Sure. Could it be 6? 6, 7, 8, 9. That works. Could it be 7? No. Because 7, 8, 9, 10. D cannot be 10. Because D is just one digit. Right? So A is anything between 1 and 6. So I'll literally have to plug in 1, 2, 3, 4, 5, 6, see which one gives me a divisibility by 9. Because look, A could be 1, 2, 3, 4, 5, and 6. Cannot go higher because then it breaks down on that consecutive clause. Well, but again, we haven't discussed how we can carry out digit, but all we know that first 4 consecutive, well, 0 does not come after 9, right? 0 is on the other hand. But anyway, so let's just do it in our head. If I plug in 1, I get 4 times 1 plus 6, that's 10. 9 divides 10? No. So that doesn't work. 2, 8 plus 6, 14, doesn't work. 3, 12 plus 6, 18. Does 9 divide 18? So that works. 4, 16 plus 6, 22. Does not work. 5, plug in 5, you get 20 plus 6, 26. Doesn't work. 6, no. So the only option is 3. So if A is 3, what is B? 4, and what is 5, 6. So the only number that we got is 3, 4, 5, 6, and 0. So here's a number. It's a 5-digit number. First 4 consecutive, divisible by 45. Check this out. 3, 4, 5, 6, 0, divide by 45. We got something, So that's actually the only number that we got. But that's just case 1. Now we'll have case 2. Case 2 says change 0 to 5. Well, let's try that. But we can use a lot of the same arguments already. Case 2, E equals 5. So that means our number is A, B, C, D, 5. Okay? So we can make that previous argument. We have that 9 divides A plus B plus C plus D plus 5. Because now instead of 0 we have 5. And again, if I replace B with A plus 1, C with A plus 2, D with A plus 3. Yeah, right. So therefore, 9 divides 4A plus 11. Okay? Now we'll do the same thing, right? So let's try. So again, A could be anything from 1. So A could be 1, 2, 3, 4, 5, 6. So 1, does 1 work? 2, does 2 work? Well, no, 2, it's what, 8 plus, yeah, 2 doesn't work, sorry. 3. Did 3 work? 4? You said 4 works, right? Because you get 16 plus 11, 27. So 4 works. 5? No. 6? No. So 4. The only one works. Just 4. So then the number is 4, 5, 6, 7, 5. Only 2 numbers that are divisible by 45, but first 4 digits are consecutive. And all of infinity. Out of all 5-digit numbers. But kind of cute, right? Just kind of but this is kind of the big thing to realize. If the numbers are consecutive, that means a plus 1, a plus 2, a plus 3, starting with a. And then we also, that saved us a little bit of time. There are other time-saving tricks as far as, in order for it to be divisible by 9, it has to be divisible by 3, so you can start with that. But, if you only have 6 options, just plug everything in. And it's pretty simple to compute. Is that okay? Wasn't that fun? Okay.
Why does that first one work if they're technically not all?
But only 4 have to be consecutive. Remember, only 4 have to be consecutive. Right? That was the part. Yeah, 5-digit numbers, there is only 4. 4 does not need a in the end. So, I don't know what that came from. But, I know, plenty of that stuff. Okay. Let's prove that square root of 2, well, we haven't defined irrational numbers, but we talked about this briefly. Rational numbers, what are the rational numbers? The ones can be expressed as a fraction, as a ratio of 2 integers. Integer on the top, integer on the bottom. So that's a rational number. Even if you have a number that has a decimal that goes on forever, could still be rational if there is a repeated pattern. So like 0.33333 forever is 1/3. Okay? Basically, yeah. So any is 5 rational? Yeah, it's 5 over 1, 10 over 2. So every number, remember how we played with that? Every natural number is an integer. Well, now every integer is also a rational number, because you can always put it over 1 or whatever. And then you have all your 2/3 and -7/5. So those are rational. We like them. So the definition of rational numbers so those are numbers that can be expressed as a ratio of 2 integers. So some examples would be, 1/2, -3/7, 2 1/3, 5 itself. So every integer is a rational number, and every traditional fraction is a rational number. And again, things like 0.33 forever, also rational. Numbers like 1.4564564566 forever, like that, is rational. There is a way to flip it into a fraction. It's hard, but if there's this kind of repeated chunk just goes on. Not just a pattern, because there are numbers that have patterns, but they're not repeated patterns. Like, for example, if I give you this number, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, right? There is a pattern. What am I going to write next? 0, 0, 0, 0, 1. That's not the pattern that I'm talking about. This might still be might not be rational. Okay, but if there is a repeated pattern like that, then it's rational. Now we have a special symbol for the set of rational numbers. It's a capital Q with a little twist. Q for quotients. So kind of fun to use Q to represent rational numbers. Okay? But unfortunately, there's also a set of irrational numbers, the numbers that cannot be expressed as a ratio of two integers. So the ones that have that infinite decimal with no real patterns goes on forever and ever. Okay, so irrational. So it cannot be expressed as ratio of two integers. Decimal goes forever with no patterns, no repetition. We don't really have a symbol for irrational numbers. Some books would use capital I, but we use capital I for imaginary sometimes, a set of imaginary numbers. So, because we don't, I mean, they're fun, but there's some stigma attached to irrationals. Some of the examples, do you know some? Square root of 3, that's what you have to prove on your homework. Have you done that already?
No.
Okay. Square root of 3, square root of 2. Any combination, like square root of 2 plus 1 over 7 would be irrational. If it just has that thing. There's some more famous irrational numbers. Pi is one of those. Pi is irrational. E is definitely irrational. And again, any combination, E times 5 plus 7 over pi, that's irrational. Actually, this is the weird statement. There are many more irrational numbers than rational numbers. Both are infinite. But irrational numbers carries a much grander infinity than rational. It's weird to think about this, but we can actually, there's a way to count rational numbers, kind of put them in order. You would be the first rational number, and you would be the second rational number. And if I come up with a scheme to lay them out like that, I can actually able to, hypothetically, to do all of them. Put the rational numbers in order. Impossible with the rationals. So there's weird statement, but this infinity is much heavier than the one before. Anyways, well, but that's because, but both of them are infinite, right? So there's, it's a sneaky thing. But yeah, so the story goes, you know your Pythagorean theorem, right? So there was this guy, Pythagoras, ancient Greece. So they had this society called Pythagoreans, and they just did a lot of math. It's going to be like our math club. We can call ourselves Pythagoreans or whatever. But, and they really, so it's back then, you know, ancient Greece, they believed in that world is perfect. You know, rational numbers, everything can be expressed as a ratio of integers. They wrote music based on, you know, every note is a fraction or whatever, it's perfect. And you know, ancient Greece, so, you know, Olympics, all that stuff. And then amongst their group, there was one guy who went, hey, look at that, square root of 2. It's real, because I can build a thing that's square root of 2 feet long. That means I can find a point on the real number line. Okay, this is square root of 2 right there. It's a square root of 2, whatever units away from the origin. So it's real. I can experience it. But I can never write it as a ratio of 2 integers. Therefore, it's not rational. So there's something else out there. So they tried to kind of keep it a secret. But he was talking, and they actually killed him. Yeah. Well, I think the legend is they took him to a sea, and they came back without him. And nobody ever seen him again, the guy with the square root of 2. So nobody knows what happens to him, but...
I don't want to be part of your math club now.
Hey, I'm not saying we're... but I'm openly talking about these secrets. Now, here's the thing, how he was able to construct. Do you know how to construct square root of 2? It's really straightforward. You can go to the, your whatever, Home Depot, 1 and 1. You need 2 sticks, 1, and the other one is 1, and you lay them with a 90-degree angle. And then you take another stick and you just cut it from here to there, like that, right? You can take a very long stick and then you just make a cut. Well, then by the Pythagorean theorem, right, a squared plus b squared equals c squared. So that means 1 squared plus 1 squared equals c squared, right? Well, what is 1 squared? 1, so 2 equals c squared, therefore c is square root of 2, right? So I can construct square root of 2. It's going to be very hard for me to construct pi or e. Those are unconstructible, but they're very complex proofs why they're irrational. But we can do square root of 2 really simply. We can show that square root of 2 is irrational. But it's real. Irrational numbers are still real. So here's the proof. Have you seen that, before I go into the proof, that funny little cartoon where, you got pi and I, and they talk to each other? Yeah. This one says, be rational. And this one says, get real. Isn't that fun? Pi talks to I. Yeah. So that's kind of stuff we might do in math. Well, yeah, we're also going to have like a math joke of the month club. The driest one wins. So anyways, proof that square root of 2 is irrational. So this is a really good and juicy example of proofs by contradiction. That's really the first proof by contradiction you should experience. And since we already have done a little contradiction, you know a bit of a plan. We're going to do it by contradiction. So remember how the contradiction works. You assume the opposite, because a real number can either be rational or irrational. There's no third option. That's the nice part. Because really the set of all real numbers is just all rationals with irrationals glued together. That's the set of real numbers. So if I'm trying to prove that square root of 2 is irrational, and I want to do it by contradiction, what am I going to assume? Square root of 2 is rational, right? I'm going to assume the opposite. So for the sake of contradiction, assume that square root of 2 is rational. So we're going to assume that, and we're going to do some math, and at the end we're going to come to a place that makes no sense. We're going to come to something that's definitely wrong. So we're going to say, well, that's a contradiction. Therefore, the assumption is wrong. Therefore, it's not rational, it's irrational. But, so let's just go with that. If square root of 2 is rational, by definition, it means that we can express it as a ratio of 2 integers. That's what it means for a number to be rational, right? So therefore, there exist, let's say, numbers n and m, both integers, so that square root of 2 equals n over m. Remember that fancy notation? So there exist. That means 2 integers. Capital Z is the fancy symbol for integers. So square root of 2 can be written as a ratio of n and m. Okay? Now, I'm going to make a little note, and this note will become very important. N and m have no common factors. They have no common multiples, meaning they're relative prime. Because if they do have a common multiple, I can always reduce that fraction. You know what I mean? If this was like 12 over 36, I can reduce this to 1 over 3. I can always reduce a fraction to a point where I can no longer reduce it. Is that okay? So note, n and m have no common multiples. In other words for that, n and m are relative primes. With respect to each other, they're prime numbers. They have no common multiples. That makes sense? Because if they did, we can always reduce it. Okay, so let's play with that. So, since square root of 2 equals n over m, I can get rid of that square root by squaring both sides, right? If you square both sides, you get 2 equals n over m squared, which really gives me 2 equals n squared over m squared. Is that okay? And I can keep going with algebra. Therefore, n squared equals 2 times m squared, just multiplying both sides by m squared. Is that okay? So n squared equals 2 times m squared. So that means, by definition of even numbers, that n squared is an even number. Can you hear that? Therefore, no, because n squared equals 2 times something else, right? So clearly n squared is divisible by 2. Now, actually this also implies, and we're probably going to have to prove it later because we haven't done that. It implies, if n squared is even, actually implies that n is even as well. Do you believe that? If square is even, the number itself is even? Well, odd times an odd. No. Odd plus odd. Well, let's do this on the side, because this is, we cannot just say, well, that makes sense. Let me do this really fast. Let's say, don't write this down. It's a really simple proof, I believe. N is even if and only if n squared is even. Actually, it's not that simple to prove. But anyway, so two-way street, right? If and only if means I need to do two things. So first thing, if n is even, then n squared is even. That's easy to prove, because, and don't write this down, I'm going to do it really fast. But if n is even, since n is even, that means I can write it n equals 2k. That's what it means for something to be even, right? So therefore, n squared equals 2k squared, which is 4k squared, right? Is 4k squared even? Yeah. I mean, I have to get all very precise. It's 2 times 2k squared, where this is some other integer, m. So it's 2m, so it's even. So we're done with that part. Yeah. So that part is done. Now, going backwards, if n squared is even, then n is even. That one is a little trickier. Okay, well, we can do that one by contradiction, actually. It's going to be very fast. Assume that n is not even. Therefore, n is odd, right? Therefore, n equals 2k plus 1, right? Remember the odd numbers are 2k plus 1. So therefore, n squared equals 2k plus 1 squared, which is 4k squared plus 4k plus 1. Right? That's how you square a sum. Remember that formula? You should. Yeah, we spent a lot of time on that. Or you can just FOIL 2k plus 1 times 2k plus 1, and you FOIL that. Out of the first two, I can pull out a 2. 2k squared plus 2k plus 1. So that's, if this is some m, this is 2m plus 1, therefore n squared is odd. That's contradiction, n squared is even. Right? So contradiction, therefore n is even. All right, good. Are you okay with that? You're giving me the look. Yeah, well, square means multiply by itself. So it's 2k plus 1, 2k plus 1. So if you FOIL this, look what happens. 4k squared, 2k, 2k, 1. So that's 4k. Okay, so good. So therefore n is even. Is that okay? So therefore, there exists a k among natural numbers or integers so that n equals 2k. Right? Since n is even, I can always write it as 2k. Is that all right? Okay. So I'm going to take this fact and I'm going to substitute it in here. Because now n equals 2k. So by the way, you can now use this. N is even if and only if n squared is even. And we can do the same thing for odd. That works for odd too, right? N is odd if and only if n squared, because you might need that for the cube roots or something like that. But not the cube roots, but the square roots of 3. So anyways, if I take 2k and plug it in n squared, we'll get 2k squared equals 2m squared, right? I just replaced, in that statement on the right, I replaced n squared with 2k squared. Is that okay? So if I take it further, this is 4k squared equals 2m squared. Is that okay? So divide both sides by 2. I'm getting m squared equals 2k squared. So m squared is even. Do you agree with that? Because I just expressed m squared as 2 times some other number. So therefore, m squared is even. Therefore, m is even. Right? So no matter what, n is even and m is even. Is that possible? Can I have a fraction where numerator and denominator are always both even? Well, if I do that, what can I do with that fraction? I can reduce it, right? Remember this thing, that m and m have no common multiples, right? Because I can always reduce it. But now, well, this tells me no matter what I do, I'll get a fraction that always has an even number over even number. And I reduce it, and it's even over even, and I keep reducing, right? So that's a contradiction. I cannot have a fraction, so we're contradicting this little note. I cannot have a fraction that has common multiples forever and ever. No matter how hard I try to reduce it, there's always something left to reduce. It actually means both numbers are infinitely even, so they're both zeros. So if 0 over 0, first of all, is a bad number, right? And nowhere near equaling square root of 2. So that,
So that works then? So you're not contradicting the initial statement, you're contradicting the note.
yeah, I'm just contradicting some basic rule of math right
Yeah,
now.
but that note is a basic rule of math.
Yeah.
Like you have to reduce it to 1/3 or 2 over 3.
I know, I understand that. It's that. So by contradicting an element of the problem that you're trying to prove, or
Yeah.
by contradicting an element of the proof, you contradict the assumption made before.
Right, because again, you've seen like here, and I understand what you're saying. Here, the contradiction came from the part of the problem, initial statement, but your contradiction can come from the very basic rule of math as well. You say like, well, if I assume that, then I'm violating some really simple rules of math. And this was one of those, that I cannot reduce fractions over stuff. That's what I just got to. That no matter how hard I try, I'll get a fraction that has even numbers on top and bottom. So I just kind of changed math all of a sudden, so I shouldn't be doing that. So here, this is a contradiction. M and N have no common multiples. Therefore, assumption was wrong. So square root of 2 is not rational. So therefore, square root of 2 is irrational. This is a very nice proof. It's pretty complex, but on your homework, you'll have to do square root of 3. So you basically change this whole thing. You're going to get, basically you're going to end up with m and m always divisible by 3. No matter how hard you try, you won't be able to reduce them. It's always going to be multiples of 3. That's your contradiction. We're here till 10, right? Okay, good. But does that make sense? So this is the contradiction proof. Okay. Oh, yeah. That one is off. Computer clock is off. That one, did they fix that one? Yeah, that one is like 10 minutes fast. This says 9:33. Yeah, it's a little like a minute slow. I trust that clock. Okay. Okay, so you will need this for the homework, and you'll see those statements again in the future in this class. We're actually slowly moving towards something that we'll use. So a few more definitions. LCM, least common multiple. So the definition, so LCM of two integers, so least common multiple of two integers is the smallest integer that is divisible by both. So LCM is really your least common denominator. When you're looking at two fractions and you're trying to find the least common denominator, you're looking for least common multiple. The smallest integer that's divisible by both numbers. Okay. Here's the notation that we use. If you ask to find the least common multiple of two numbers, so let's say here are the two numbers. 16 and 18. So you want to find the smallest integer out there that is divisible by 16 and divisible by 18. You can trial and error your way to that answer. Sometimes it's hard. But really, all I'm asking to find is the least common denominator. We have two fractions, like 3 over 16 plus 5 over 18. What is the least common denominator? You know the proper way of finding that?
Just trial and error.
Yeah, because it can get really, what if I make numbers bigger? Trial and error you might get stuck. Yeah, it will work, but it won't be the least common. It will just be a common multiple, right? So here's the trick. The first step, do prime factorization of each number. Break it down into products of primes. So write okay. So 16 is easy. 16 is 2 to the power 4. So that's 16 as product of primes. While 18 is 2 times 9, which is 2 times 3 squared. So this is the prime factorization of each number. By the way, prime factorization is unique. You cannot have two different prime factorizations for the same number. So prime factorizations are unique. So now think about this. We're looking for, in order for our number to be divisible by 16, it has to be divisible by 2 to the power 4, right? If I look at these primes, basically all I have to do is just to take the highest power of each prime. You see, 2 to the 4 is still divisible by 2, so I don't need that extra 2 in there. All I need is 2 to the 4th. So I'm just going to take each prime raised to the highest power. So all I need is 2 to the power 4, and 3 is another prime, so I need the highest power of 3 is 2, so I need 3 to the power 2. So whatever this is the least common multiple of 16 and 18. So that's what? 144? So 144 is the smallest number that's divisible by 16 and 18 at the same time. Okay? So at the same time, when we talk about least common multiple, we talk about greatest common factor. That's another notion, GCF. So greatest common factor of two numbers, of two integers, is the largest integer that divides both numbers. So least common multiple is the smallest that's divisible by both. The greatest common factor is the largest that goes into both. So we can actually do it the same way. If you look at the prime factorization, think about this. What is the largest number that divides both? Yeah, it has to divide 18 and 16. If you just look at the primes, you know 3 is out of the question because 3 does not divide 16. Because there's no primes of 3 in there. The only number that they both share is 2. And you look at the smallest one now. So it's only 2 to the power 1 that divides both. So the process is very similar. You're going to take prime factorization, then take the lowest powers of the primes that they share. So there's two numbers that both share a 2, right? And the lowest power of 2 right now is 1. So 2, that's the greatest common factor. So that's the largest number that divides both. So again, prime factorization. And 2, take the smallest powers of common primes. So in this case, GCF of 16 and 18 is 2. Because that was the common prime between them was 2, and the lowest power of it was just 1. Does that make sense? There's a little nice, cute property. We're not going to prove it, but there's a property about the LCM and GCF. If I take LCM of two numbers and I multiply it with a GCF of two numbers, I'll actually get the product of those two numbers. And you can just kind of check it with this one. 144 times 2 is 288, right? And 16 times 18 is 288. So the product of least common multiple and the greatest common factor is the actual product of two numbers. Yeah, it's a good way to check it. Let's do this quick example. Just pick two numbers. So GCF of 15 and 18 and LCM of 15 and 18. So regardless, we have to do prime factorization, right? So 15, that's easy, 3 times 5. 18, we already did 18, it's 2 times 3 squared. So the GCF is 3. Now for LCM, remember, we need to take everything. So we need a 2, and we need a 5, and we need the highest power of 3, which is what? So it's 2 times 5 times 3 squared, so that's 10 times 9, so that's 90. So the LCM is 90, the GCF is 3. And 3 times 90 is 270, and 15 times 18 is also 270. So does that make sense how to find this? I think you have a few homework problems. We'll ask you to... Did you have homework problems that were asking you to do that? Yeah. LCM and GCF for these numbers. Okay. Okay, we've got to talk a little bit about absolute value. I got some absolute value questions there. We have time for that. So absolute value again, it's kind of a review. You've all done absolute value before. You all understand how to compute absolute value, right? If I ask you what is the absolute value of 5, you will say 5. And if I ask you what is the absolute value of -3, you will say 3. And if I ask you what is the absolute value of the square root of 2, you will say square root of 2, right? Is that okay? What if I ask you what is the absolute value of 1 minus square root of 2? where did that come from?
Because if it's a negative number, then we have to multiply by negative.
Very good. Because if you think about this, how do you compute absolute value? You look at the number itself and you think, okay, it's positive, so don't mess with it, right? If a number is positive, then the absolute value of that number is that number, right? Absolute value of 5 is 5, absolute value of 12 is 12, absolute value of square root of 2 is square root of 2. But if the number is negative, how did you compute the absolute value of negative 3?
Well, I guess so.
Yeah, right. That's the only way you can make something positive. You just multiplied it by negative 1, right? So when you look at the number 1 minus the square root of 2, is that number positive or negative? It's going to be negative. Square root of 2 is bigger than 1, so 1 minus square root of 2 is negative. In order to make it positive, multiply by negative 1. So it's negative of 1 minus the square root of 2, or square root of 2 minus 1. That's what you actually get. Right? If you distribute the negative, 1 becomes negative, square root of 2 becomes positive.
So would you just put like double descriptions of like definitions of absolute value?
Not really. The definition of absolute value is like this. It's that piecewise function. It's negative x if x is less than 0, and it's x if x is greater than or equal to 0. I mean, maybe that's what you meant by definition. So yeah, we're defining it as a piecewise function. So if the number is negative, change the sign. If the number is positive, let it be. You all know the graph of the absolute value function, right? From algebra, what is it? It's a v. But if you think about this piecewise function, here's a line, slope is 1, intercept is 0 for positive, so that's the line, right? This is the x. Well, this is negative x, right? So it's the slope is negative 1, works for the negative domain. Slope is positive 1, works for the positive domain. So you still get the v. So this is how we compute absolute value. If the number is positive, let it be. If the number is negative, change the sign by multiplying by negative 1. Because, you have problems. Here's a fun one on your homework. Computing those absolute values. You just have to identify, is square root of 51 minus 7, is that positive? Probably. Because, square root of 51 is bigger than 7. And here's the square root of 75 minus 11. That's probably negative. So you're going to have to change the sign of that. Okay? Now, when you look at the problems like question D or question C, let's try questions. I'll do question C for you. Square root of, so this is from your homework. Square root of pi squared minus 8 pi plus 16. So I want to simplify that. Now, first, you notice something good about pi squared minus 8 pi plus 16. Is there a quick way, a nice way to factor that? What is it? Yeah, it's a square. Two numbers that multiply to 16 add up to negative 8. So it's pi minus 4, pi minus 4. So it's pi minus 4 squared. That's what that factors into. Well, how do we take a square root of something squared? Almost. You have to be very careful. The square roots, no matter what, always produce positive results. By definition, square root is positive. Do you remember the graph of your square root function? So this was the absolute value of x. Do you remember the graph of the square root function? It's like that, right? So it's never negative. Square root cannot produce negative results. But now, if we go back to what you were saying, just chop off the powers, I can do it here, right? Square root and the power 2 will kill each other. I'll get 7. I'm okay with that. But if I give you square root of negative 7 squared, if you follow the same logic, You'll get negative 7. If you just ignore everything else and you just kill the square in the square root. Can that happen? No. And you kind of realize this, if you follow the order of operation, you'll have to square first, so that's a square root of 49, kills the negative, and then that's 7. Right? Right. So that's clearly we need to develop something else. So we cannot just do the, you're exactly right. If I start squaring first, I'm back where I started. But you notice that it almost works. You just have to make sure that it comes out positive. So it's really the absolute value of what's on the inside, so you get 7 in both cases. The actual definition of the square root of a squared is absolute value of a. So that will guarantee that the answer comes out positive. Okay? And this is the very important thing that students usually forget, that with the odd powers you can do whatever you want, because the cube root can come out negative. But with the even ones, you have to make sure if you cancel the power before you do anything else, just make sure that the answer comes out positive, and that's the absolute value. So then if I use that, this comes out as absolute value of pi over 4. Oh yeah, but we can keep going, right? Because now we can take the absolute value. You have to judge, is pi minus 4 positive or negative? Negative. Pi is less than 4, right? Pi is 3 point whatever, so pi minus 4 is less than 0. To make it positive, multiply by negative 1, so that really becomes 4 minus pi. So that's the answer. No absolute values, no radicals. And it comes out positive. Does that make sense? We kind of use two properties here. First, we really had to review the fact that you don't just cancel the square roots and the squares. You have to make sure that the answer also comes out positive. And the absolute value takes care of that. And then we reviewed how to take the absolute value. If the number on the inside is negative, then you literally just flip it around the minus sign. And we can just, for fun of it, since we have a little bit of time left, I can plug this number on the left in the calculator, pi squared minus 8 times pi plus 16. Whoa. And I need to take square root of that, right? Here we go. Is that okay? Who can memorize that number? I'll just put it in the memory. And this one is a lot easier, right? 4 minus pi. That looked pretty close, right? I'll subtract it from memory. So then when I recall memory, I should get 0. Well, that's 0. Right? It's negative 37, so that's 0.370 some junk. So this is the rounding here. Okay? I mean, this is 0. Yeah. Cool. All right. So I think that's it. You should be able to do your homework. Again, don't hang up on the proofs too much. I'm just having fun with that. I won't be putting any proofs on the tests or anything like that. Maybe as an extra credit.